what we're going to do today is have a look at some stuff around AC circuits. So AC circuits part 1, I've titled the session. We're going to look at AC circuit conditions for per resistance, per inductance, and per capacitance. And then we're going to look at when we have inductive and capacitive, and look at the terms inductive and capacitive reactance, the impedance of a AC circuit. We're going to use phasor diagrams to describe these conditions, and we're going to look at solving some AC circuit problems. And we'll be continuing that next week. Right, so first of all, purely resistive AC circuit. So if we take a circuit with a single resistor, connect it to an AC supply, a current IR will flow, and there will be a volt drop, VR, across that resistor. Yeah. We can draw what's called a phasor diagram, okay, and I'll qualify that a little bit more when I've shown you the others. But we can draw that the voltage. Phasor diagram shows the magnitude of a quantity and its direction or angle. Yeah. And in a purely resistive circuit connected to AC, the voltage VR and the current IR are in phase with each other. They're at the same angle, always, for a resistor. So if we then draw the waveform of the voltage and current on the same axis, on the same time axis, we have the voltage and the current peaking at the same time. They both cross zero at the same time. They're in phase. And we talked a little bit a couple of weeks ago about things that are in and out, AC waveforms that are in and out of phase. So always, when it's just resistance, voltage and current, with that, in terms of that resistor, are in phase with each other. And these two lines on this phasor diagram are only separated from each other, so that for clarity, actually you draw them on the same line, if you're drawing an active diagram. Okay. Everyone happy with that? Now, before we go any further, we need to consider a slightly different term for the opposition to current flow that we would if we were talking about DC circuits. In AC circuits, we use a different term for the opposition to current flow. That's called impedance. It's got the symbol Z as opposed to R, but it's still measured in ohms. So you can think of the impedance as being the equivalent of resistance in AC, and it can be used in Ohm's law and all the other formula. In place of resistance, we can use impedance. Right. However, the difference between those two, between resistance and impedance, is resistance is what's called a scalar quantity. All it has is magnitude, a size, 10 ohms, 20 ohms, 1000 ohms. Okay. Impedance, on the other hand, is a vector quantity. That means it has a magnitude, but also an angle at which it acts. And so it's expressed like this at the top bottom. Because resistors have a zero angle, they're in phase. That's the in phase component. We'd express ZR as R ohms. That bit is the magnitude of resistance. That's called the magnitude. And then we have the angle. And that can be degrees or radians, depending on what the angles and the problem are. Yeah. Okay, so we always have the magnitude followed by the units if appropriate, then the angle symbol, and then the angles on the end. And the degrees part, if you're working in degrees, is important, because if you take that away, the assumption is that's radians. So without the little degree symbol, you would assume radians there. Okay? You're all happy with that? So from expressing just resistance in ohms, we're now gone to impedance, where it is the resistance in ohms at a particular angle to express impedance Z in ohms. Now, if we consider what would happen if we could have a purely inductive circuit connected to AC. In a purely inductive circuit, the current IL lags the applied voltage VR by 90 degrees, or pi over 2 radians. So here's our circuit with an AC voltage. Current IL will flow, and we have a voltage VL across the inductor. But when we draw the phasor diagram, if we consider VL as the in-phase component, the one at 0 degrees, 0 degrees is always left to right there in our axis, 90 degrees is straight up, 180 is there, and this is 270, or more applicably, minus 90 degrees is what we're more likely to work with. So positive angles around anti-clockwise around the top half of the circle, and negative angles that way. But the positive direction is always anti-clockwise. So as VL at 0, our current lags is behind in time because time has gone round anti-clockwise, so it's downwards. So we have a minus 90 degree angle associated with the current in a purely inductive circuit. Right. One thing should be pointed out, however, is that pure inductance is not achievable in reality in a real circuit, because the coil that makes up the inductor is a coil of copper or some other wire that has some resistance as well. So you cannot possibly get a real circuit that is inductance only. If you could, that would be how it would behave in an AC circuit. And this current lag is happening because of what you were looking at when you looked at the self-inductance last week. As the voltage is rising, the current's trying to rise quickly, and the back EMF, do you remember that term from last week? Is forcing it down. So that's what forces this current to lag behind the voltage. Voltage goes high, current tries to go high really quickly, but makes a big back EMF, so it makes that full 90 degree phase shift in the current. All right? All happy with that? So, must be remembered that inductance causes current to lag voltage by 90 degrees. Now I've got an easy way for you to remember this in a minute coming up. All right. Now, related term, inductive reactance. In a purely inductive circuit, the opposition to AC current flow is called the inductive reactance, XL. We can calculate the magnitude of XL if we know the voltage across the inductor and the current through it, so we can use Ohm's law, or we can multiply the inductance by the frequency by 2 pi. So 2 pi times the frequency times the inductance in henries will give us the inductive reactance. This is where F is the frequency in hertz and L is the inductance in henries. This has considerable implications for AC circuits with inductance, because that formula means that the reactance of the inductor its opposition to current flow varies with frequency. As frequency increases, over here, XL gets bigger. So it's not a fixed quantity. If we change frequency, the inductive reactance will change. If we change frequency, the resistance of a resistor doesn't change. Okay? So it's directly proportional, the inductive reactance is directly proportional to the frequency. As frequency go up, XL goes up as well. XL is measured in ohms, and it has a positive 90 degree angle associated with it. So an inductor has a positive 90 degrees. So we have ZL is equal to XL, the magnitude. We can calculate that from 2 pi FL. Ohms, angle, 90 degrees. Yeah. All okay? Good. So, have a go at the 2 problems. Problem 2. The coil has an inductance of 40 millihenries. So let's pull the information from the question. L is 40 millihenries. Negligible resistance. Calculate its inductive reactance. So we want to find XL. And the resultant current, find L. If connected to a 240 volt 50 hertz supply, and B So that's the information from the question. So what do we need to do first? Find current, that should be I, not L, and XL for A. Have I got the information I need to find XL at the top? How am I going to find it then? Times 10 to the minus 3 for that is the easiest way. That equals okay, I've got 5.7 here, so I'll do that. Ohms. 12.57 ohms. Yep. So how can I find I? Yep. Which is in this case R is actually XL. So that's 240 over 12.57 equals 19.1 amps. Now, second circuit, 100 volts, 1K. You have to recalculate XL because the frequency's changed. Yeah. So XL, 2 pi FL. The inductance hasn't changed, but the frequency has. So it's 2 pi times 1,000 times 40 times 10 to the minus 3. .3 ohms. Up to, and then we can calculate the current for, again that's V over XL, 100 over 251.3. .398 amps. I've got on my results here. So you're close enough. Alright, so just think about this. Just do, I don't know why, the ideal thing for me here would be keep the voltage, keep the magnitude of the voltage the same. Just do 240 over 251.3 instead of 100. Right, so we're talking about same circuit, same voltage as A, so 240 volts, same inductor as A, but 1,000 hertz as opposed to 50 hertz. We've got a difference between 20 amps and an amp, 20 times difference. And that's exactly how many times the frequency is multiplied. 20 times from 50 to 1,000. So just showing you the circuit's the same, but we alter the frequency and we get more opposition to current flow. Yep. And if we connected to a 240 volt DC supply, we'd get negligible resistance with lots and lots more current, because we wouldn't have this inductive effect all the time. So even if the resistance was an ohm, we'd have 240 amps flowing. Yep. I can give you a practical indication of the implications of the difference between impedance in an AC circuit and resistance in a DC circuit. I had some machines where I used to work that had little tiny plug-in relays. Some of them were a DC coil for 24 volts DC solenoid, and some of them were for 24 volts AC. If you put an ohm meter on the coil of the DC coil relay, you'd measure somewhere around about 50, 60, 70 ohms. If you put a DC meter on the AC coil, maybe about 3 or 4 ohms. All right. If you replace the AC coil relay mistakenly with a DC one, the circuit won't work. It won't energise because the impedance is too high. However, if you do go the other way round, you put the AC one in the DC circuit, that relay will work for a long time. Depending on how often and how long it's energized for, it will work. But eventually the coil will burn out. We had a problem where someone replaced a DC coil relay with an AC one, worked for a small while, faulty again. Take that one out, 24 volts AC, put another 24 volt AC coil in, and so it went on until somebody actually got the drawings out and checked and made sure, hang on, this should be a DC relay, and then the problem was solved. So there are significant differences in that practical situation between the DC resistance of two coils and how they work in circuits. Right? Are you all okay with that so far? So we've got quite a few new quantities coming in here. Inductive reactance XL, calculated with 2 pi FL. Alright, we've also got currents and voltages out of phase with each other. There's quite a bit, and I wouldn't think too many of you have done this before. Is anyone who has? Like AC causing currents and voltages out of phase? Yeah, okay. Right, so that's an inductive circuit. Now we're going to consider a purely capacitive circuit. Now, when you connect a capacitor to a DC voltage, the capacitor plates charge up, and then eventually there's no current flow. It blocks DC current. However, if you connect a capacitor to an AC circuit, the plates, as we go in the positive half cycle, plates charge up, positive and negative, then they discharge as the current starts to go the other way, and charge up again, positive on the right hand side, negative on the left hand side, and so on. And on the AC mains they do that 50 times a second. What that causes is, in a purely capacitive circuit, the current IC leads the applied voltage VC by 90 degrees. So exactly opposite to that of the inductor. In the inductor, the current lagged. In the capacitor, the current leads. Alright, and if you had a pure capacitor, which again is not achievable because the leads and the plates have got some resistance, if you did, you'd have exactly 90 degrees phase difference between current and voltage. And here we've got the voltage is the blue waveform, the in phase at 0 degrees, and the current is 90 degrees ahead. The peak is 90 degrees ahead of that for the voltage. Alright. Should be noted that that's not achievable because of the resistance of the conducting wires and leads. Okay. I'm going to add a slide here and help you with this, a way of remembering whether currents and voltages lead or lag each other. Right. Capacitive circuits, current leads voltage. So in that word civil, because current comes before voltage on the capacitive side of that word, current, you would say current leads voltage. We just now done that. The current had a positive 90 degree angle. And then in the inductive circuit, voltage leads current. Or equally, we could say, here we could say current lags voltage because it comes after. Alright? So that word will always be a check for you as to whether you've got it the right way round, whether you can remember what causes leading and lagging. Okay. Now there is a proviso on that, and that is when we get to a circuit that's got both components in, a capacitor and an inductor, and possibly a resistor as well. Okay. The circuit will still be either overall inductive in nature because the inductive reactance is bigger. We're coming on to this next week. Or it'll be overall capacitive because the capacitive reactance is bigger. These two quantities work against each other. And so it's which one's the biggest that takes over. So in a capacitor, sorry, go on. And that's L for inductance. Yeah, in Henry's. That would have been a bit confusing if that was I again, wouldn't it? Alright? Yeah? Okay, so civil's the word to use if you want to help you remember which way round they are. Right. So, in capacitive circuits, current leads the voltage. Capacitive reactance. In a purely capacitive circuit, the opposition to AC flow is called the capacitive reactance, XC. XC can be derived from voltage across the capacitor divided by the current flowing, using Ohm's law, or it is 1 divided by 2 pi FC. Because the fraction is on the bottom of the frequency is on the bottom of that fraction, it means that as frequency increases, capacitive reactance decreases. The 1 over or inverse relationship. So this is where I said XL and XC work in opposition to each other. Alright? Capacitive reactance varies with frequency and is inversely proportional to it. The inductive reactance has an angle of minus 90 degrees associated with it, such that the impedance in an inductor, ZC, impedance of a capacitor, that should read, that's what happens when you copy and paste and don't edit properly. Impedance of a capacitor is XC, the magnitude in ohms, angle minus 90 degrees. Okay? Right, 2 problems on capacitors in AC circuits. 5 minutes, plenty of time. Bash them, mate. Right. Part A, XC, 1 over 2 pi FC. That's 1 over 2 pi times 50 times 10 times 10 to the minus 6 per micro. Guys, please. $318.3 ohms. B XC 1 over 2 pi FC. That is 1 over 2 pi times 20 times 10 to the 3 times 10 times 10 to the minus 6. Remember, right up front we learnt these indexes used for multiples and submultiples. 0.796 ohms. Second question. We've got a capacitance value of 23 microfarads. That's 23 times 10 to the minus 6. farads. V is 240 volts. F 50 hertz. Now, we can do this separately like the other question, but equally we can do it all. We can say I is V over XC, because we can say that's equal to the voltage we've been given divided by 1 over 2 pi FC. We can do the calculation all in one go. But that way we don't round that figure and then carry that round into the overall calculation for current. So we've got 240 volts divided by 1 over 2 pi times 50 times C, which is 23 times 10 to the minus 6. And that comes out at 1.73 amps is what you should get. Right? Everybody happy with that? Good. RL series circuit. So what we want to consider now, those per circuits, per capacitance, voltage across, the current as the reference phasor in red, voltage across the resistor as the in phase with the current in blue, the voltage across the inductor is 90 degrees ahead of the current. Does that work right with the word civil? Inductive circuit, voltage ahead of current. Yeah. Okay. And then that means Vs is the vector sum of those two voltages. We create a parallelogram between the two and then go across the diagonal. That represents the voltage Vs, and it has magnitude length that's going to be longer than either of the other two, and it has an angle phi in there with the current. Okay with that? Yeah. We can from that derive a voltage triangle where we've got VR on the horizontal at the bottom, we've got VL 90 degrees to it on the vertical, and then Vs is on the hypotenuse. So we can calculate the magnitude of Vs using Pythagoras theorem. It's the square root of VR squared plus VL squared. Alright, and we can find the angle using the inverse tangent. The tangent of the angle is the opposite over adjacent. You should remember that from school. Okay, so if we take the inverse tangent of that ratio, we'll find this angle in here. So that's the voltage triangle. We can also have the impedance triangle. That's where R is on the horizontal, XL is vertically upwards, and then the impedance is the vector sum of the two. And that has magnitude Z, angle phi. And those two angles, whichever data you use to calculate them in the same question, are going to have the same value. Yeah? Okay? So Pythagoras theorem and a little bit of right angle triangle trigonometry will allow us to do those calculations on circuits with resistance and inductance in series. So let's have a look at a problem together. In an RL series circuit, the potential difference across resistance R is 12 ohms. So let's write that out. VR 12 volts. So VR is 12 volts. Potential difference across the inductance, so VL is 5 volts. Find the supply voltage and the phase angle between current and voltage. So we want to find this phase angle. Now, when we work on these kind of problems, it's always worthwhile to draw the triangle and the information you know on that triangle. So here we've been given voltages. So we want to work with a voltage triangle. There's VR, and we know what that equals. It's 12 volts. Yeah, voltage across the resistor. There's VL. We know that equals 5 volts. We know that angle in there is 90 degrees. And then we can complete the parallelogram and say that is VS. And we want to know that angle in there. Yeah. So we go by Pythagoras. Vs is root Vr squared plus Vl squared. That is root 12 squared plus 5 squared equals, I think you'll find that's 13 volts. Yeah. Yeah. Using the tangent ratio, theta is equal to, or phi is equal, sorry, tan to the minus 1 of, yeah, opposite over adjacent, yeah, 5 over 12. Yeah. How do I fully qualify that angle? How do I fully qualify that angle? How would it be in terms of the current? We know it's an inductive circuit, so the current is ahead, so the voltage must be lagging. Yeah. Lagging, because that's an inductive circuit. The voltage must be, says that, the question says, find the supply voltage and the phase angle between the current and that voltage. Alright, so we calculated the voltage and that's lagging the current. It must be, because it's an inductive circuit. Alright? Alright? Let's have a look at the second one, see what it says. Coil has resistance of 4 ohms. Inductance L equals 9.55 millihenries. Okay, and one way of representing an inductor that has a resistance of the wires that you can measure is that you draw them as a resistor in series with an inductor, and that whole thing is the inductor with its resistance combined. Alright. Calculate the reactance, so we want to find XL. That's A. B, find Z, the impedance, and C, find I. V is 240 volts, 50 hertz. Where are you going to start with that question? Oh yeah, you're going to start. So how do we calculate it then? C is find, you've got to find A find XL, B find Z, C find the current. Sorry, fine. Well spotted. Why can't you use 2 times pi times? No? No? Yeah. Because under the conditions, you can't calculate reactance without the frequency. Unless you knew, you could get it if you knew the current, but you don't know that either. So 2 pi FL take the -3, remember, for milli. Three ohms. So that's part A. B, how are we going to find Z? What could we draw here? So we can draw a triangle. What value goes on the hypotenuse? Now we're not a voltage triangle now, are we? We're trying to find the impedance. Which one is the in-phase component in terms of impedance? Which one goes horizontal on the impedance triangle? R, yeah. R on there. What's the horizontal component? XL. So the hypotenuse is Z. Yeah, to get the angle, we want to know the magnitude as well. So you're going to do R squared plus XL squared. Four plus 3 square rooted. I think you'll find that's either 3, 4, 5 triangle. And as you say, you need to complete that off. We must have the angle as well. So phi in here. Tan to the -1 of 3/4. So 36.87 degrees. No, we don't say that's lagging. That's wrong. Just that. Okay, and then C whoa. What's the overall opposition to current? We've got R, this is our circuit, it's a resistor and an inductor in series to an AC supply. Yeah, so we've got to add together R and XL, but they're not in phase with each other. So that's what we've done with the triangle. Z is the overall impedance of that circuit. Z's the overall opposition to current flow. So let's do V of a Z. So the magnitude of the current is 240 over 5 equals 48 amps. And then the angle is what we calculated earlier, 36.87 degrees. And because that's inductive, it's a lagging. C-I-V-I-L. Current lags voltage. Right, for the remaining 15 minutes, yeah, no, you don't finish at 1:30, you finish at 1:45, right? For the remaining 15 minutes, there's 2 more problems for you to have a go at. When you get an answer, the problem 8 is an interesting one because it gives a demonstration of how you might be able to find the inductance of a coil. If you connect it to a DC supply and measure the current, you can calculate the resistance, and then connect it to an AC supply and measure the current. You can calculate the impedance, and then you can use the triangle to find the reactance, and then the formula to calculate its inductance. So that's what that first question is around. And then the second one is another one similar with a few little bits added to it, to what we've already done. So have a go at these 2 questions. When you get an answer, just say to me, have I got it right? I'll have a look and see if you're right as you go along. Okay? Over to you.